Hi, my name is Ethan Black,
And my name is Fisher Thompson.
and this is our microcontroller final project. For this project, we decided to build an instrument cluster that would ultimately be able to be used with the Baja SA buggy. I am a part of this year's senior capstone, and one thing our customer wanted was a system that was able to log the temperatures inside the CVT cover and ultimately find out why our belts are slipping. This project is a good first step to getting this data for the Baja team.
The way this project helps contribute to Baja is by having a full instrument cluster with 4 subsystems: a temperature monitoring circuit, an engine RPM Hall effect circuit, a vehicle speed Hall effect circuit, and the LCD module. These subsystems have different styles of sensors to log the data that was needed. First, a TMP36 analog temperature sensor was used to monitor the CVT temperature. We chose this sensor for its simplicity and because it outputs a voltage directly proportional to the temperature. That made it easy to interface with our microcontroller's ADC without needing extra wires.
Before we get into testing, we want to quickly explain how each subsystem actually works. Because this project is really about applying everything we learned in the course to real hardware on a vehicle. For the first subsystem will be the TMP36 temperature sensor. It outputs a voltage that changes by 10 millivolts per degree Celsius with a 500 millivolt offset at 0 degrees Celsius. We feed this voltage into ADC1 channel 5, which is pin PA0 on the nuclear board, as you can see here. Then our microcontroller converts that analog voltage to a 12-bit digital number, and our code converts that into a temperature value. The TMP36 is wired by using a 3.3 volt source, as you can see here, a signal wire, which is sent to PA0, and a black ground wire. This subsystem is important to the Baja team because the CVT normally gets extremely hot during long runs, and knowing when the belt starts overheating can help prevent belt failure and performance loss.
Both the RPM system and the vehicle speed system use unipolar digital Hall effect sensors. These sensors detect changes in magnetic field. When the magnet passes in front of the sensor, the output flips from high to low, creating a clean digital pulse. On the vehicle, we mount a small magnet to the rotating shaft or wheel. Every rotation produces 1 pulse. To measure RPM and speed, we use the STM32's timer input capture feature. For engine RPM, we use timer 2 on PA5. For vehicle speed, we use timer 3 on PA6. Each timer measures the time between pulses. Once we know the period, we calculate RPM equals 60 divided by the period, and speed equals the wheel circumference times rotations per second. This approach gives us accurate and real-time measurement without needing interrupts on every edge. The LCD setup is similar to that of our previous labs. The LCD is connected from PB0 to PB3 for data, PB4 and PB5 for control. The LCD also has a higher refresh rate to give the most accurate data from the sensors.
For our first test, we set up the vehicle speed sensor on an RC car as shown here with the Hall effective magnet on the wheel. And then also the vehicle speed on the LCD will show on the side of the RC car as shown in the picture. Now here's a video of the actual miles per hour moving on the LCD as the RC goes forward. Next, we also have the track as shown here. We have the start marked by the Lego and the speed sign. And then as we come down to the end, we can see that it ends at about 79 inches with the little curl marking the end. Here is the first actual moving test of the RC car. As you can see, the RC car is coming by and passing the track, and we can record that. Here's a slow-mo with an average speed of about 3.96 miles an hour on that test. And look at that brake job right there. It was close to the wall, but whatever. We also did additional tests, but right here it shows this is a 3.96 miles an hour at the end. And here we'll show an additional test. As it comes by, we look at the ending average velocity is around 4.04 miles an hour. Now to calculate this, we showed the timestamps at around 9.27 seconds and 8.16 seconds. And doing these calculations, as shown on the screen, we got the actual miles an hour in the test compared to our calculations to almost be dead on, showing that this is an accurate mile an hour reading on our LCD. For our next test, we decided to test the accuracy of the CVT temperature. For this, we have our LCD showing a temperature here and our TMP36 in a cup of water with the K-type thermocouple. And for the thermocouple, it's hooked up to a TC08 and into Picolog6, our software, as you can see here. And to do this test, all we had to do is compare the temperatures as shown on Picolog6 to our LCD. And as you can see on there, it is about 18 and varying a little bit higher, up to 19. And let's see our LCD screen. As you can see, this one is a little bit more steady at around 18 degrees C. And we keep these here just to see if they'll be a little more accurate towards each other. And as they sit here, you can see the LCD is pretty close to the K-type thermocouple at around 18 degrees Celsius and dropping same as the LCD. And that pretty much proves our test for the CVT temperature. We will want to install this on the CVT in the future to monitor the slipping of the CVT when it gets above a certain temperature threshold. And this will be shown to the driver through that LCD, and pretty valuable data for the Baja team. For our final test, we are testing the RPM on the actual buggy itself. As you can see, we have a magnet attached to the output shaft on the CVT, and we will place the Hall effect sensor just above that to read the RPM gauge, or read the RPM. This will display on the LCD here, and then we'll compare the values showing up on the RPM gauge to the values on the existing RPM gauge, as you can see here. Now we'll start the buggy and show that process. All right, now we have the buggy started. As you can see here, the shaft is spinning at the RPM that we need. And to compare it, we're looking at about 1,000 RPM, which is pretty accurate to what we have. It looks like we're a little too far. There we go, right on the sensor, showing the RPM here. And to compare that to the existing RPM gauge, we can see right at about what we're seeing of 1,070 RPM.
After these tests, we can conclude that we have a functional and accurate instrument cluster that could be put on the buggy with some additional changes, like longer wires and robust mounting hardware for harsh testing. While this project works with just these few sensors, it is also capable of being customized with additional features like oil temperature, battery, voltage, and any other sensors, unlike the current system on the buggy. Anything you can measure, you can put on the display.
Another future upgrade we plan on adding is a data logger. Right now, our cluster only works by showing live data values. With the data logger, we could add an SD card module or some sort of interface that the Baja team could record RPM, speed, and CVT temperature during testing, which will help them further diagnose belt slipping or any drivetrain issues that would be important for the Baja team. In conclusion, this project really pushed us to apply everything we learned this semester, including ADCs, timers, interrupts, digital interfaces, and debugging real hardware.
We successfully integrated 3 subsystems and 1 output subsystem into a single working embedded system. More importantly, we gained hands-on experience designing, testing, and validating real sensor systems.
This was a great introduction to embedded system design, and we're excited that it can actually help the USU Baja as a team moving forward.